Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy giving the lecture for microprocessor class, lecture number 26 part 2. Lecture number 26 part 2. We still discuss the floating point representation, but here we want to highlight. So in the last lecture we highlighted the different ranges of values and how the floating point is different than the fixed point or the sine tooth complement representation, the integer representation, and how the range of values is different, and how the spectrum of values are different between the two representations. Here we want to highlight in this part 2 in lecture 26 we want to highlight very important things related to the accuracy of the floating point and the problems that may occur while you are doing some simple mathematics for the floating point. So we actually wanted to cover in this second part three things: the accuracy in the mathematics, and the needs for rounding some numbers in order to represent the results for the mathematics. We need to highlight that how can the overflow case may occur for you while you are doing your mathematics. Interestingly, the floating point may also experience what we call the underflow problem. So the overflow, as we already know from digital logic design for integers, if you are performing some mathematical operation and the result cannot fit at the same number of bits for your number, so that means you have a case of overflow. The overflow can happen also for floating point if you are getting out of range. However, another thing that can happen also for the floating point is what's called the underflow, which means that the number cannot is smaller than the smallest fraction that can be represented by your representation. We already covered the range of values. So if the number that you want to represent is smaller than the smallest number that can be represented by the floating point, that means it's an underflow case. Otherwise, or if it is greater than the largest number, that means you have an overflow. We will start first by discussing the accuracy in mathematics, and again, to make the discussion simple, we wanted to start off by discussing a simple example, not even in the binary, but even we will discuss the example as if we have a storage of decimal numbers. Again, we will use or utilize the decimal numbers in order to demonstrate and make the idea clear for you. Okay, so to get the feeling about what's going on in the floating point. If I'm assuming that the mantissa that I have, assume that I can store numbers in decimal, and the mantissa has only slots for 4 digits. If I'm assuming the example that we have here on the slide, this example here is indicating that I have 4 digits for the numbers. Okay, and you can see nicely that I have 2 numbers, and each of them can fit perfectly in my storage or in my 4 digits. So the first number is 99.99. The digits of the number here, the mantissa, needs only 4 digits or 4 slots of storage. Similarly is the second number, which is 0.161, which actually needs even only 3 slots in the storage. However, if I wanted to add those two numbers together in decimal without even going into the floating point representation, the result of this addition should be simply 100.151. it is clear from the result that you can see here that, so the result as you can see it here, okay, so although this fits in 4 digits, this number fits 3 digits, the results of adding those two numbers together needs 6 digits. How can I store the result in 6 digits? This is impossible in the storage provided or given that I have only 4 digits. Definitely here that I need here to compromise, so I have to sacrifice some of the accuracy for the results, so and to do what's called the rounding, as we will see. So let's go over the steps. Okay, assume that I want to normalize the numbers with the most significant digit, okay, will be after the decimal point, and the rest of the number before the decimal point or to the right of the decimal point. Assume the same thing here, so I have 1.61 is actually how can I represent the number. So in floating point, if I'm to store the numbers here, so the first number will fits exactly in my 4 slots. Okay, so I have here 4 slots, and I have 9 9 9 9 9 9 9 9 stored in the number, and the exponent should carry the value 1. For this number I have 4 slots, and those 4 slots will carry the number 1610, and the slot for the exponent should have -1. So now let's discuss how can I do mathematics for those numbers. Okay, so first of all, I have the numbers as stored in the format like what they are shown here. Okay, so if I am about to add those two numbers together, okay, the first condition is that I cannot go ahead and add the numbers directly. Okay, I have for the first number 9.999, the other one is 1.61. I cannot add the mantices together because actually I have unequal exponents. Actually, the first step that I have to do in order to add those two numbers together, I need that the smaller number, the number with the smaller exponent, to match the exponent for the other number, and I can achieve this by simply adjusting the number. Okay, in order to make it I have to have equal equal exponents. In order for this exponent to equal the exponent of the other number, this decimal point, okay, should be shifted to the left for at least 2 places. So the exponent for the first is 1. I have to subtract from it the exponent for the second, which is also 1. So that means the total shifts I have to do is 2. So that means I have to shift the decimal point to the left 2 locations. Definitely this is an unsigned or magnitude, so I can add 0 here, and shifting the decimal point 2 places to the left, which allow me to raise the exponent by 2 to match the other one. So actually the number would be, okay, after the shifting will be 0.01610 multiplied by 10 to the power 1. Now I have a matched exponent with the other number. Now I have the two numbers are aligned. Okay, this process is called the alignment of the exponents, or equalizing the exponents together. Okay, so once I have the two exponents equal, okay, once I have the two exponents equal, that means the two mantisses are aligned to each other and I can start the addition. So first of all, this process of alignment caused me to lose some precision of the small number. Remember that I have only 4 slots for the number, including the digit after or to the left of the decimal point. So actually, in order to preserve this in the same storage as the other number, I would only take those 4 digits from the number and I will leave away, I will discard this, which is the first rounding that I have to do. So accordingly, here the small number here is now fits into the same number of digits as the other number after the rounding, and I'm ready to do the addition. Now I will add the two mantisses together. 9 plus 6 is 5. Then I have 1 in the carry. Then 1 plus 10 is 1, and I have no carry. I have a carry. Okay, this is actually 1. That means this is 11, 1 and a carry out. 1 plus 9 is 0 and a carry out, and 1 plus 9 is 0 and a carry out. So I ended up of this result. Okay, now since we have to store the result as normalized, that means the result could not be stored as it is. I have to readjust or normalize the result. Normalizing the result means shifting the decimal point. Okay, I have to shift the decimal point, okay, one place. I have to shift the decimal point one place. So this decimal point should be shifted one place to end up of an aligned result. So the result will be 1.0015 multiplied by 10. When I shift this to the right, I have to raise the power of the exponent by 1, so that means it's to the power 2. Okay, so again, remember that the slots that I have to store the numbers are only 4. So that means I have to make another sacrifice to round this number to make it fits only in the 4 digits available for my result. 4 digits only. I have 4 digits only. So accordingly, in the slide here as it shows, as you can see here, so after getting the result and I normalized it, okay, I have to round it to make it fit into the correct answer, to the correct number of bits. This second rounding, since I have 1.5, so usually we round this up. So this is round up. Okay, so 1.5 will be converted to the value 2. Now I have 4 digits and I have the exponent is 2. Okay, so if we need to repeat this alignment, we may repeat it multiple times. However, you can notice now that the result that I get is 1.002 multiplied by 10 to the power 2, which is basically 100.2. However, the correct answer should be 100.151. This is rounding that I forced to do it in order to adjust the result, and this is due to the two things, the rounding that is done to one of the numbers before the addition and another rounding that have been done to the result. So now based on the steps that we have just mentioned, we need to highlight the steps for the mathematics, especially addition and subtraction for numbers in floating point. So if I ever give you two numbers, okay, like that, you cannot go ahead and add the mantises together. The first step is that you have to adjust, you have to align first, okay, and this process is called alignment. You have to have an equal exponents between the two numbers. So in the second example, or in the second slide, so to align the floating point numbers, determine which exponent is the smaller, and you have to subtract the two exponents and shift the mantissa of the number with the smaller exponent, the smaller number, to the right, means shifting the decimal point to the left, and increment the exponent by 1. You have to repeat this until the two exponents are equal before you go ahead and do the addition. Shifting the smaller number to the right will discard the lesser significant bits, which is actually a sacrifice or rounding that you have to do while you are doing the mathematical operation. There are four main steps to adding or subtracting floating point numbers. First, check for 0. This is if you are adding to 0, that means there is no addition. It's a trivial step. Align the mantises, add or subtract the mantises together, and normalize the result at the end. Three major steps: alignment, addition, then normalization. So let's take one more example here, and starting from the early stages. Let's assume that this is a very simple or a very demonstrative example. I have two numbers, 0.5 and 0.25. Those two fractional numbers, I want to put them in a floating point representation with some specification. Assume that I have 6 bits for normalized fractional mantissa. That means 1 bit for the sign, 5 bits for the fractional mantissa itself, and I have 3 bits for the biased exponent. So we are having here a very simple toy model of the IEEE standard. Definitely the IEEE standard using a much more number of bits for the mantissa and exponent, but for the demonstration here we're using a way smaller number of bits. First of all, since he mentioned the biased exponent, this may be correct, or it is the time for us to mention how can I learn the biasing. Okay, if you still remember, for the IEEE standard, the exponent has 8 bits, and we concluded that we have, in order, after we trimmed the two special cases when the exponent is all zeros and when the exponent is all ones, okay, which are the special cases. Definitely here I have to have 8 of them, and here also 8 of them. So in those two special cases, this is for infinity and not a number. This is for the 0 and unnormalized numbers. Okay, so after excluding those, we have actually, okay, the range of values from minus 126 till positive 127. So if you still remember that we mentioned that the biasing for IEEE, biasing was 127. So what is the golden rule for the biasing? The golden rule for the biasing is that, so by analogy here, so the biasing here was 2 to the power a number of bits of the exponent minus 1 minus 1. Okay, so 2 to the power 7 minus 1, which is 127. So the golden rule or the general rule is 2 to the power n minus 1 minus 1. So accordingly, this is the general rule. Okay, so in this example here I have 3 bits, so that means the biasing, the first thing I have to calculate mean the biasing. Okay, biasing based on this rule, it is 2 to the power 2 minus 1, which 3 minus 1, which is 2, minus 1. 2 to the power 2 is 4, minus 1, that means the biasing should be 3. So I have to add 3 to the value of the exponent in order to bias it. Following the steps for the floating point in order to perform the operation. So our next step is to solve this example. So now we need first to convert the numbers that we have from their decimal representation into the binary representation. So 0.5 converted to binary will be 0.1 in binary. Okay, definitely this is multiplied by 2 to the power 0. The power of the exponent is 0 in that case. Okay, so if I wanted to normalize it, that means I have to shift the, I have to make a shifting to the decimal point, or the binary point should be shifted by one place here in order to make the number as 1.0. Then that means shifting to the right means I have to reduce the power by 1. So that means I have actually to have, so my mantissa here is 1.0. that means the real mantissa after I discard this one, if I am following the IEEE standard. So that means, and as we mentioned, we have 5 bits for the fractional mantissa. Here are the 5 zeros after discarding the 1, and I have the sign is positive, so the sign bit equals to 0. So this is the S, and this is the fractional mantissa, and the exponent is minus 1. And from the last slide we mentioned that we have to bias it by adding, so minus 1 plus 3 equals to 2. So 2 in binary is basically 0, 1, 0, and we have 3 bits for the exponent. Okay, so this is the exponent field. Now we will do the same thing for the other number. Again, convert it from decimal to binary. Okay, let me just indicate that here. So this is the number decimal, here converted to binary. Okay, so we convert it from decimal to binary, then we multiply it. This is 0.01 in binary, and again here I want to normalize, so I have to shift the binary point 2 places to the right, means I have to lower the exponent by 2. Okay, so I have the number as 1.0 as well. So accordingly this is the fractional mantissa, okay, F, and I have the exponent is minus 2. Minus 2 plus 3 equals to positive 1. That means I have to put it as 1, 0, 0 in the 3 bits. This is actually my my exponent. Definitely the sign is 0. This is how I store those two numbers. However, if I want to do mathematics between them, I want to add those two numbers together, so I actually have to bring back the one that we have discarded just for the representation. We have to bring it back into the numbers here, because this is part of the result, part of the numbers. So never forget this step. Never forget to get or to return the one back before math. Okay, because this is part of the numbers. So I have 1.0000, 1.0000, the first one with the exponent 0, 1, which is 2, and the second with which is actually 2, the second with exponent 1. Okay, and they have an unequal exponent. So in order to add those two numbers, I have the exponent should equal each other. So accordingly, I have 2 minus 1 equals to 1. That means the number with the smaller exponent should be shifted. The decimal point should be shifted to the left for one place. Should be shifted to the left for one place. Accordingly, the exponent should be raised by 1 or incremented by 1 to have an equal exponent. Okay, so accordingly, going to the second slide, we can see here that we shifted the number and we ended up of the two exponents are equal. So the two exponents now are equal. Okay, and we are free to add the two mantisses together. So adding the mantisses will give me, so step number 1 is the alignment, step number 2 is the addition. So I end up of this result. The result does not need any normalization, so I can take the number as it is. So store the number back into the floating point, take this as your fractional mantissa, discard the 1 again, put the number back into the mantissa here, floating point mantissa. The exponent is does not need any adjustment, so it is 0, 1, and this is the sign bit. The number is already normalized. Agree? So now let's discuss another example and to see what will happen, or can we ever have an overflow case or not. Okay, so using the same setup, assuming that I need to take another example. Okay, let's take another example. So now I have the example now, want to add 0.5 to 0.5. Okay, so we repeat the same steps as before. So the representation for the first number and the second number are the same, 0, 0, 0, 0, 0, 0, 0, and 0, 1, 0, 0, 0, 0, and 0, 1. Okay, and those numbers are not 0, and they already aligned. Go to the addition. I have actually exponents are equal. Adding the numbers. After adding the numbers, the result is not aligned. Since the result is not aligned, not normalized, I have to shift the decimal point 1, or the binary point 1 place to the left, which means I have to raise the exponent, which is the exponent here is definitely 0, 1, 0 for the two numbers. So the result has 1, 0, 0, 1, 0. So I have to raise its exponent by 1. So I end up of exponent 1, 1 instead of a 0, 1. So adding 1 to this, I get this, and this is how the number will be stored at the end of the day. Okay, in the floating point representation. So here I need normalization, not like the previous example. Let's take one more example. Here I have the numbers at 8 and 8, the same mechanism, converting 8 to binary, definitely 8 in decimal, converted to binary, so I have 0 0 0 1 in binary. Okay, so accordingly, so this is actually multiplied by 2 to the power 0. So I need to normalize it, so that means I have a decimal or a binary point here, and this binary point should be shifted for 3 places to reach this location, correct? So accordingly, this number equals to hold a second, this number actually after the shifting equals to 1.000 in binary multiplied by 2 to the power. When I shift it to the left, I have to raise, okay, the exponent by 3 places, so increment it by 3, so 2 to the power 3. So this is actually the number that we have here, about 1.000 multiplied by 2 to the power 3 for both of the numbers. How can those be stored? I have 3 unbiased, I have to bias it, يبقى هنا biasing exponent biasing. 3 plus 3 equals to 6. This is in decimal, so in binary it is 0 1 1 in binary. Okay, so the exponent for each of the numbers would be 0 1 1 0 1 1, and after discarding this one I have the mantissa. So this is actually the mantissa, the fractional mantissa, and this is the biased exponent, and this is actually the sign. Okay, so now the two numbers have already aligned, the numbers are aligned, so I can just go over the addition directly, because here is for both of those numbers the exponent is 0 1 1 0 1 1. Now after the addition, when I add those two numbers, I end up with this number which has the exponents also a 0 1 1. Right now I need to normalize the number. When I try to normalize the number, that means I want to take this and shift it by 1 place. That means I want to raise the exponent by 1. When I add 1 to 0 1 1, I ended up of the exponent 1 1 1. We agree before that 1 1 1 in the exponent is reserved for the infinity, okay, or not a number. So that means I have here a case for what? A case for overflow. Okay, so there is an overflow here. The results cannot fit in the same number of bits as for the floating point representation provided. Okay, definitely mathematics, further mathematics like multiplication is even much tougher, okay, and also the division. So we will not go over either multiplication or division. We will stick only to the addition and subtraction, but right now you are ready to solve the assignment number 5. So I encourage all of you to go ahead and solve all the problems for assignment number 5, which I will post and will solve some of its problems inshallah in a next lecture, in the one of the upcoming lectures. But right now you are ready to solve all the problems for assignment number 5. Okay, see you in the next lecture, lecture number this is 26 part 2. In 27 part 1 we will go and discuss some of the hardware for the floating point units, which is actually used in hardware, which we didn't discuss yet, and some of the instructions. So we'll talk in more general about the floating point units and the hardware for performing the floating point, because actually all of the hardware that we have discussed for the x86, for the 8086, is not performing any of the floating point. It's only for integers. How to perform operations in floating point, this is what we will be covering in the next lecture, inshallah. Thank you, and see you soon in lecture number 27.